Unfortunately, that means you might have to go to the podcast to get that first part. What had we written? We had said moles I C sub pi is equal to the sum of C sub pi times Na0 times theta I minus stoich of I over stoich of A times x sub A. Okay, so where we had left off, we're going to take that n sub A0 and pull it out to the front, out in front of the sum. It's the same Na0 everywhere, so that's that. And then we're going to take the C sub pi and distribute it to each term. So the C sub pi times the theta, that's not going to look particularly different. So if we rewrite that, we have n sub A0 out front times the sum of theta I times CPI. All right, so that's distributing the first one. Then we distribute the C sub pi onto everything else, the stoich I over stoich A times XA. So that's, put it over here. Notice if we multiply that out, if we multiply heat capacity of I times that term, we have another one of those special groupings, which looks like a heat capacity of I times a stoichiometric coefficient of I. That's another delta. So that's delta Cp. Defined, the same way we had delta H, delta G, delta, I can't remember another one that we had, delta Cp. That's that one. And so that becomes the second one that's coming along over here. Delta Cp divided by the stoichiometric coefficient of A times x sub A. Right, so this is going to become our denominator. Oh, that shouldn't be a square bracket. It should be a round bracket. So I think on the next slide I'm going to end up, actually we might as well put it in there right now. The energy balance ends up being everything that we saw before. So dt. We haven't changed anything in the numerator. Do I want to write this right now? Yes. Q dot minus a bunch of stuff. I'm not going to write that bunch of stuff just yet because we're going to make a modification there as well. But the only thing that we changed with that last derivation that I just gave was this. The denominator, instead of Ni times Cpi, we pulled everything out and made it in terms of A. So that's why we've got this theta I times Cpi, and then minus the delta Cp, divided by the stoichiometric coefficient, times xa. I'm just going to put another parenthesis there in case anybody thinks that xa is actually on the bottom. It's not. All right, so all we did there is rewrite the denominator, again in terms of A. Again, this is mostly useful if you've got a single reaction. If you've got more than one reaction, it's not really worthwhile to rewrite things in terms of A, but it does help make the subsequent math a little bit easier for a single reaction if you do that. Oh, yes, thank you. That's nu sub A. Because the nu sub I got stuck inside the delta. Oh, man. Sorry about that. Why didn't I write the top part, the delta H term? Because the delta H term is a function of temperature. So we saw actually it can be a fairly strong function of temperature when we were dealing with like the K1 term. We had said if we do the shortcut K, the equilibrium K, it's just K0 times K1. If the enthalpy is not a function of, if the enthalpy is not constant, we needed that whole K2 term. Whether that's significant or not, it's hard to tell before you actually start the problem. But we're at the point where I said earlier, the assumption of heat capacities being constant does actually make everything simpler, but this is where it makes it look like it may have gotten a little bit more complicated. The reason for that is because the change in enthalpy now looks like this. So if we know the enthalpy at any particular temperature, it doesn't matter what temperature we happen to know it at, I'm going to call that subscript R as any old reference temperature, right? If somebody gave you an enthalpy, you looked up the enthalpy of reaction in kcalc or something like that, and you want to adjust it for a temperature, that looks like this, delta Cp times whatever temperature the reactor happens to be working at minus that reference temperature for the enthalpy times Ra over the stoichiometric coefficient of A times the total volume V. So the big change that I just did without deriving it, we did actually derive that expression a minute ago when I had said this. This term here. We're using that term again, that relationship that enthalpy is associated with a rate of change of temperature times heat capacity. We have used that again here to say if I know the enthalpy at one temperature, a reference temperature, I can adjust it to any other temperature by multiplying it by delta Cp times T minus Tr. That's not bad, right? We can do that if the heat capacity is constant. The problem with that becomes it's not consistent with what we said for K2. When we had written K2 for an equilibrium coefficient, or sorry, an equilibrium constant, we did not assume that Cp is constant. We said it was a full function of temperature. And so it's possible to get into a situation where you're using two different assumptions for Cp in the same problem. Right? If you use K2 as it's given in kcalc, that assumes that this is the polynomial form for delta Cp. And yet we've just said for every energy balance we ever write, we're going to use delta, or sorry, every Cp is constant. So we need to fix those two assumptions. Or sorry, not fix them, make them consistent with each other. We're going to change one of them. This is the one that we're going to use, that Cp is just a number, it's constant. And so in order to use that effectively with the equilibrium information we learned previously, we have to tweak that K2 a little bit. As you've seen in most of your homework problems, K2 doesn't come up all that often, so it's not going to kill us. But we will have a couple of cases to deal with. So that's the energy balance. If you're going to, don't memorize energy balances, just write them down. But that's a good one to have written down because it's going to come up pretty often. The challenge here is that not only is temperature changing, it's changing with a function of time, but also, oh, that was supposed to be green. The conversion of A is changing with time, and typically your reaction rates, these, are also changing with time. Actually, slightly worse than that. The reaction rate itself here is not just a function of time, it's also a function of temperature. And it's for these reasons, among others, the Q is also a problem, that we end up not really being able to solve any of these by hand. We have to go dump them into MATLAB because multiple things are changing at the same time. And with only a very few exceptions, can we ever actually solve that thing by hand. The other expression that we need, the other differential that we need to solve in addition to this, apparently I left my equal sign off. This is not times all of that. It's equal to. The other differential that we have to solve in addition to this is the material balance. And so that becomes the second equation of our coupled equations that we have to solve. The initial condition for this, which everything with batch reactors, actually everything with flow reactors, only deals with initial conditions. The initial condition of this is that T of any time 0 is equal to T sub 0. All right, we just say the reactor starts out at 200 Kelvin. 200 Celsius. Whatever the number happens to be, an initial condition always comes along with that. You can't solve the problem until you know what the initial condition is. The other expression, the form that we generally use, you can use the dNi dt term that was the most general one. For example, if the volume is changing, you would have to use that. very commonly, the other expression that we end up solving for in this particular expression, or this particular system of problems, is that the change in conversion, XA, with respect to time, is minus RA over NA naught times V. Wait. Yeah, that's, yeah, I think that's okay. Yeah. NA over V, CA naught. Yeah, that. If we're going to use this, V is constant. Not difficult to get a constant volume in a batch reactor, much more difficult when you get to a flow reactor, because there you're not talking about constant volume of the reactor, but rather the element of gas anywhere in the reactor, which is free to expand in two directions. And so that becomes somewhat more difficult to deal with. And the initial condition for this is that the initial conversion, XA naught, is always 0. Not always, but in most cases it's 0. In order to solve that, again, we need MATLAB, because we have to solve those two differential equations simultaneously, because they're both changing as a function of time. And that's something that MATLAB doesn't struggle with, but if you had to do it by hand, it's kind of difficult. If on an exam, for example, I would have you do something with thermal effects, that could be one of the ones where you have to code in MATLAB. So I would give you a sheet that looks like MATLAB lines, and you'd have to write the solution there. Or I would start giving you so many assumptions that we eventually get to the point where we can solve one of them analytically and substitute it into the other. It's usually more that you have to solve the MATLAB stuff, like write the MATLAB stuff. If you want an example of what that looks like, again, I think at the end of exam 2 that's been posted, you can see what that kind of a question looks like to solve something in MATLAB on an exam. So that's that. Those are the two equations. If you look at the homework that's going to be posted today, most of them are solving this equation simultaneously with this equation for different assumptions, different systems, et cetera, et cetera. Finding data from different places. So I had mentioned that delta HR plus delta CP times T minus TR was not entirely consistent with the equilibrium K. Here's how we handle the equilibrium K. Do I want to talk about... Yeah, we might as well use the full thing. Let me think. Sure. So originally we had said that we can approximate the equilibrium conversion, or sorry, the equilibrium constant K as K0 times K1. That approximation holds if delta H is constant. What we have just learned, though, is that delta H in general is equal to the enthalpy of reaction plus delta Cp times T minus Tr. That's where that substitution came from in the previous expression. So if we're going to use the shortcut K, which is what we have up there, K naught times K1, and we know that we are now assuming that the enthalpy of reaction changes is according to this particular equation, the only time that delta H is exactly equal to a constant value is if delta Cp is exactly equal to 0. So if delta Cp equals 0, this implies that delta H is equal to a constant. And if that's equal to constant, then we can use K shortcut. So our equilibrium K becomes K shortcut. What does that look like in practice? Most of the time it would look like I give you a K at some temperature, and I give you, for example, an enthalpy of reaction, and we use this form of the shortcut. So log K2 over K1 is equal to delta H Is it log? Yeah, I wrote it wrong in my notes. I was looking at it. It looked funny. R over T1, 1 minus T1 over T2. That's the common form that we will end up using. But strictly speaking, we can only use that form if we calculate that delta CP is exactly equal to 0, because this form, which is another form of that shortcut K that we have up on the top, assumes that delta H is constant. And so that's the form that we will use most often. How do we know if CP is constant or not? Or sorry, if delta CP is 0 or not? If you look at that little sheet that I passed around towards the beginning, the problem statement, look at the heat capacities for A and B. I've said they're equal to each other and they're 100. So they're both constant and they're equal to each other. And so the delta CP for that term would be exactly equal to 0. And we could get away with this shortcut version that we've got here. I did say that they're equal to each other, right? Okay, good. The other way that I could get around something like this, I mean, not that I can get around it, and I could give you a problem that's reasonable to solve, is I could just flat out tell you that K is constant. This is not an assumption that we typically make if we're really trying to solve something reasonable. It's not uncommon as a problem statement for a homework or an exam. So these are the two options that we generally have. So either I will give you heat capacities in such a way that delta CP is equal to 0, and you can use the shortcut version that I've got here as the first bullet, or I will just tell you the K that you're interested in is constant. And then you don't have to worry about whether the heat capacities are equal to everybody or that delta CP is equal to 0. You just sort of override everything and say, all right, he's making the problem a little bit easier, the K's are always constant. If that is not the case, if you end up finding out that K is not constant, nobody has said K is constant, and the delta CPs are not equal to 0, or well, there's only one delta CP, then you're left in the third situation, which isn't really terrible. What we end up needing is that K2 is slightly different. So the previous version of K that we had seen, this one, the full Van't Hoff was K1, sorry, K0. K0, K1, K2. But this particular form was the one that we said all of the heat capacities look like A plus BT plus all the other stuff, right? That was the polynomial heat capacities, and K2 looked kind of nasty. What we will instead do is if you go through that entire derivation and assume that the heat capacity is constant, the only thing that changes along the way is K2, and K2 looks a little bit simpler. And so just to denote the difference between the two of these, for our particular systems that involve energy balances, if you really have to deal with the CP terms, there'll be a new K2. I'm just going to call it K2 prime. The only difference for this is that all CPs are equal to constants. And the K2 prime that we've got here actually isn't half bad. So it's the exponential of delta CP, so there's our delta CP term, times R times natural log T over T ref, whatever the reference happens to be, plus T over T ref, minus 1. So it doesn't have those enthalpy correction terms or entropy correction terms. It's just this. And as we would expect, if the delta CP happens to be 0, you get a 0 up front and the exponential of 0 is 1, and you fall back into the shortcut version afterwards. So if you really have to do it, if delta CP is not 0 and nobody has said that K is constant, you can use this K2 prime expression which isn't terrible if you put it inside MATLAB. It's one extra line that you have to write in there. And it's much more simple than assuming that the heat capacity is a function of all that nasty stuff. So again, the most common situations that we will be in is one of these two. Whoa. So these are the most common. One thing that you will never do, at least in terms of an energy balance, is you will never have to put this inside of an energy balance. That doesn't mean you won't have to use it, right? I can ask you questions that require K-calc, but you will never have to put the full version of the Van't Hoff equation inside of an energy balance, because that means you have to code the whole thing by hand. And then somewhat uncommon, although not impossible, would be this one. It would be an uncommon case if you have to use this one. I would say 1, maybe 2 times the whole year. I would ask you to do something like that. So the vast majority are the other ones. Yeah?
Is the term on the left side, is there supposed to be K or right?
Oh, yeah, thank you. That's just K. So these are both Ks on that side. We have no circular references here. Thank you. So that, again, possible, unlikely. Most of the time, you'll be in one of these two situations, either because I said take K as constant, or I worded the problem in such a way that the heat capacity is all constant and such that delta Cp is 0. There's one other tricky one, which is an irreversible reaction, right? If the reaction is not reversible, the whole discussion of equilibrium Ks is irrelevant, and so then you don't have to worry about it either. So that's another option that I could give. So to Wednesday, we'll focus on that example problem that's on there. Again, review that template for ODEs, because we're going to use it on Wednesday. Can I also have those problems and any uncollected homework back?